Hi, I'm Reuven Lerner. Welcome to my PyCon Talk Function Dissection Lab, where we are going to learn about functions by taking them apart. A few words about myself. I am a full-time Python trainer. Most days, I am in a different city, different country, different company teaching Python, everything from Python for non-programmers all the way up to advanced Python workshops. Lately, I've not been traveling so much, but I'm still doing lots of training via WebEx and Zoom. I also have a bunch of courses on my site about Python, data science, and Git, including weekly Python exercise, a family of courses to level up your Python skills. I also just published a book called Python Workout with 50 Python exercises with Manning, and my Better Developers list goes out to about 15,000 developers every week with Python tips and hints. But enough about me. Let's write some code, and then we will take it apart. So let's consider this code. I've got x equals 10, 20, 30. So I'm defining a list, and then d equals a1, b2, c3, so I'm defining a dict. And then I'm also going to define a function, hello name, return hello name. And we look at this and we figure, okay, I'm defining two variables and I'm defining a function. But Python thinks about it very differently. Python actually sees these as roughly equivalent. And we can see that most easily with the Python tutor site that Philip Guo has written. And so we see here three global variables. X refers to the list 10, 20, 30. D refers to the dictionary, A1, B2, C3, and hello refers to the function object, hello. And if function object sounds a little funny to you, yeah, function objects are kind of weird because they make us think about functions as not just verbs that we can execute and run, but also as nouns that we can use. So when you use def to create a function, you're actually doing two separate things. You're creating a function object, and then you're assigning it to a variable. So what's the advantage of knowing about and thinking about function objects? Actually, there's quite a bit. Once we start thinking about functions as objects, we can remember that functions, like all objects, can be assigned to other names. So if I already have my hello function, I can also say hello2 equals hello. And now both of these variables, hello and hello2, refer to exactly the same function. Okay, but I can also pass a function as an argument to another function or to a method or to an object constructor. This is a fun one. I can say hello, parentheses, hello. And in this example, I am executing the hello function. I'm using it as a verb, but I'm also passing it hello, the same function, as a noun to itself. So we can pass functions as arguments. It's not a problem, something we do all the time. I can also remember that all objects in Python have attributes. Attributes are these like private dictionaries that every object has. So if you have a.b, b is an attribute belonging to a. It's not a local variable. We use them all the time. And an attribute can contain any kind of object. And indeed, we're going to see they contain lots of interesting objects in just a little bit. We can get a list of all the attributes on an object with dir. Dir of hello will then return all the attributes on our function object. Okay, that's nice and interesting and all, but how does Python use a function's attributes? Well, let's define our function again. Def hello name, return f string hello name, and let's now run it. So if I call hello with world as an attribute, as an argument, what happens? Well, we get back the string hello world. So far, so good. What happens if I call the function with no arguments, hello parentheses? Well, then we get an error. And the error says that hello is missing one required positional argument, name. And my question is, how did Python know? How did it know that we were missing one positional argument, and how did it know that that positional argument was called name? And the answer is attributes. The most important attribute on a function object is dunder code, under code, under. This is sort of the heart, the soul, the brains, however you wish to describe it, of a function object. It contains the bytecodes and all sorts of hints to the interpreter about our function. Now, if you're not sure what bytecodes are, remember that Python is not an interpreted language. When we define a function, the function is actually compiled into an intermediate form, bytecodes. Those are stored inside the function object, and when we run our function, the function's bytecodes are used to execute it. And we'll talk more about the bytecodes in a little bit. So, how does Python know how many arguments our function takes? Well, the code object, dunder code, has its own attributes because it's an object and all objects in Python have attributes. And so arg_count is always going to contain an integer indicating how many arguments the function takes. So hello.dundercode.co_arg_count shows us 1. That's right, the function takes 1 argument. And so when we run the function, when we run hello world, Python says, okay, co_arg_count says we need one argument. The user passed one argument. All is good. But what about when we call the function with 0 arguments? What's going to happen? Well, Python is going to say, co_arg_count says we need one argument. We didn't pass any arguments. Error. That's why we get the error. Now, what about this name? How does Python know that our argument was supposed to be assigned to the parameter name? Well, you won't be surprised to hear that there is another attribute involved. We're going to be talking about lots of attributes here. And that attribute is co_var names. Parameters are local variables. They're not defined inside of the function body, but they are still defined and they are still local variables. And co_var names is always going to be a tuple of strings, each string being the name of one of the local variables. So if we look here at co_var names, we're going to see that it's a tuple with one element, one string, name. So Python now knows that the function requires one argument. And that argument is going to be assigned to name. And if we get no arguments, the name is missing a value. And sure enough, when we run hello without any arguments, we get the error message, hello is missing one required positional argument called name. What if our function has 2 parameters? Def hello first and last, return hello first and last. Well, if we look at arg_count, it's going to be 2. And if we look at co_var names, it's going to be first and last. And so error messages use this information. We see it all the time. If I call hello now with this 2-argument version, hello with Reuven, I'm going to get the error message saying, no, hello is still missing one required positional argument called last. And what if I try to be a smart aleck about it, right? And I don't just pass a positional argument, I pass it as a keyword argument. Hello, last equals Lerner. Well, it's going to say, no, you're still missing one positional argument called first. And what if I try calling the function with A, B, C, 3 different arguments? It's going to say, no, you can't do that because hello takes 2 positional arguments and you provided 3. By the way, what if I define a local variable as well? So let's just change our function a little bit. So now instead of returning the string right away, we assign it to a local variable s. Well, when I look at arg_count, co_arg_count, it's going to show me that co_arg_count is still going to be 2. We're still only taking 2 arguments. But var names now contains 3 elements, first and last, and s. So the parameters to a function are always going to be the first few elements of co_var names. How few? Whatever it says in co_arg_count. Yeah, but we have some other kinds of parameters that we haven't really described with this system. For example, what about splat args? Splat args, as you might know, takes any additional positional arguments that no one else wanted. So here if I define hello, first, last, splat args, it's always going to be a tuple. And so here if I call hello of A, B, C, D, E, A is going to be assigned to first, B is going to be assigned to last, and all the rest of them are going to be assigned as a tuple to args. That's really convenient. And so if I look now at co_arg_count, what am I going to see? Actually, 2. It doesn't see args as a regular parameter. But if we look at co_var names, so args is a variable. It is a local variable. It's just not as part of the argument count. So what's going on? How does Python actually know that it's supposed to be doing this sort of assignment? Well, here we have a little bit of magic. So there is a variable called, or I should say an attribute, called co_flags. And co_flags is an integer, but it's not just any integer. It's an integer that we treat as a set of bit fields. So if you imagine it to be a binary number, each of the bits, each of the binary digits can be either 1 or 0, and it indicates whether something is true or false, on or off. So for example, 2 of these are always going to be on, optimized and new locals. These have been on for years and years and years in Python. They indicate something that was done a long time ago. But then we have splat args. So if the 3rd bit from the right there is 1, then the function has splat args. And if it's 0, then it doesn't have splat args. Similarly, if the 4th bit from the right is set on, then the function takes keyword arguments, kwargs, and if not, then not. Nested functions, if I define a function inside of another function, then this nested function is going to be, that bit is going to be turned on. And finally, if you've ever wondered how Python can tell the difference between a regular function and a generator function, how does it know whether it should execute the function or return a generator? There's a generator bit there. If that's on, then it's a generator function. So we can think of these as bits here. It's way easier in many ways to think about in hex. So I can just think of these numbers in this way, hex 1, hex 2, hex 4, hex 8. And then if I want to find out if a particular bit field has been set, I just use bitwise and compare. So if I want to know, hey, does hello take splat args? I'm going to take CO flags, use bitwise and with hex 04. Sure enough, I get back the same value, hex 04. That means that the bit was set. By contrast, if I check, hey, was kwargs set? Do we take double splat kwargs? The answer is no, we get 0 back. What if I flip it around? What if I redefine hello so that it does take double splat kwargs, but does not take splat args? So now I'm going to check, hey, does it take splat args? I'm going to do this sort of bitwise and. Nope, not there. But what if I check hex 08? Sure enough, it is there. Now, this is a really annoying, dirty, gross way to look at these bit flags. There is a better way, and that is to use the dis module that comes with a Python standard library. And dis, for like disassemble, has all sorts of functions that make it easy to sort of peek into the bytecodes of your function object. And so if I use dis.showCode, we're going to see that the hello function has all sorts of interesting information. We're not going to look at all of it right now, but among other things, it shows us the flags. And it says here, optimize, new locals, those are always going to be set. Var keywords, that is Python's internal way of talking about splat args. Our function takes, double splat kwargs, var keywords, kwargs, right? And no free, for whatever reason, it indicates this, that we're not in a nested function. Okay, fine. There's also something kind of weird here called constants. And what are the constants? The constants are when you write your function, it's translated into bytecode. Any of the literals, strings or integers or other objects that are there, are not actually stored along with the bytecode. They're stored separately in constants. And then in the bytecode, they're referred to constant 1, constant 2, constant 3. These are always stored in CO consts. That's always going to be another attribute on our function object. Now, the 0th element, the item at index 0 in CO const is always going to be none, which means that none is always available to every function. You don't need to do anything special for it. But everything else is also stored there. I also find it interesting that F strings are broken up into parts. So hello, which came before the curly braces, and the exclamation point, which came after the curly braces, are stored as separate constants. And then the bytecodes, they just refer to a byte index number. So what about the bytecodes themselves? Well, we can look at those in CO code. CO code is a byte string. I guess it's appropriate, right? Bytecodes and byte strings. And this is what it looks like for our function. Now, if that's not super readable to you, I understand. So let's use dis.dis, another function from the dis module, to look at it. And this breaks apart the bytecodes and shows us what's going on. So it's saying load constant 1. It's looking at CO consts and retrieving the item at index 1. Load fast means use a local variable. Format value, that's a format string. Load const exclamation point, so it's piecing together the string. Build string, as we can see, and then return value, so it's going to return the string. Well, as you probably know, functions can have all sorts of additional types of parameters. For example, what about defaults? So if I say def hello name equals world, now my name parameter has a default value. I don't need to call the function with an argument. But what has happened to CO arg count there? Turns out CO arg count remains exactly the same. So our function looks just like before, but we know that we can call without arguments. So how's this going to work? Well, there's another attribute, and this attribute is called dunder defaults, and it is not under dunder code. Rather, it's part of the function object, so it's sort of parallel with dunder code. And so all of the defaults are there. So let's take a look. What does hello dunder defaults look like? World, meaning dunder defaults is always going to be a tuple. If there are no defaults, then it's an empty tuple. And it's a tuple containing whatever default you set in the function definition. So we can summarize this a bit, that when Python calls a function, it compares the arguments, the number of arguments, with CO arg count. And if the number matches, great, pass the arguments, call the function, all is done. If there are not enough arguments, then we check to see if dunder defaults can close the gap. And if so, we're going to use enough values from dunder defaults to get to CO arg count. What if we have too many arguments? Well, then we're going to check CO flags and see, is splat args defined? And if so, we're just going to we're going to assign the remaining arguments to splat args, or whatever variables named in CO var names at CO arg count. Let's look at something that irks a lot of people about defaults, though. So consider this function, def add 1 of x, x.append of 1. So we're going to define a list here, my list, 10, 20, 30, and then I'm going to call add 1 on my list. What happens now if I print my list? I'm going to get back 10, 20, 31. Why? Because I passed the list, my list, to the function. The function ran append, it added 1 element to the list, and then great, the list has changed. And if I do this again, if I call add 1 again, then I'm going to get here print. I'm going to print my list, and we're going to get 10, 20, 30, 1, 1. Each and every time we call the function with my list, we're going to add one more 1 integer to the end of it. So far, so good. But let's now add a default. And this default is going to be an empty list. And the assumption is then, many people have this assumption, that now if I call the function add 1 with no arguments, we'll get an empty list assigned to x, and then the value we get back is 1. So far, so good. Let's do it again. Print add 1. The value we get back is, 1, 1. If we do it again, the value is 1, 1, 1. What's going on? So many people think that when we define a function like this, what we are telling Python is, if we don't pass an argument for x, then x should be assigned to an empty list. But that's not how Python thinks about it. Python thinks of it as, if we don't pass an argument, then it should use this empty list. That's right, it puts this empty list into dunder defaults when the function is created. Remember, dunder defaults is populated when the function is created, when it's defined. And so this list is then retrieved each and every time that we call the function without an argument, and it can change. Maybe dunder defaults is a tuple and cannot change, but the elements within it can change. So the conclusion is never use mutable defaults. Big, bad problem, you should not do it. And if you're using any sort of modern editor or IDE, it will warn you about this. And if you use pylint at the command line, it will also tell you that. It'll say, hey, you have a dangerous default value, empty list here, don't do it. There's one last kind of argument I want to look at, and that's keyword-only arguments. And these are relatively new in Python. And the idea was, what if you want to have a default value for a parameter, but you also want to have splat args? And in earlier versions of Python, you couldn't do this. So what we have now are keyword-only arguments, meaning sep here in our function has a default value of space. If we don't explicitly specify it when we call the function hello, then it will always have that default. And sure enough, if we call hello of ABC, it's hello of ABC with spaces between them. If I call hello of ABC with sep equals asterisk, then we'll have hello ABC with stars between them. So where does Python keep track of that? It's not counted with the other arguments. COArg count is 0 here. 0 because splat args is not part of COArg count, and 0 because our sep is not part of COArg count. Where is it? It's in a separate attribute altogether, COKW only arg count, and it shows that we have 1 there. So we see then that Python is checking in many places for our arguments. COArg count, it checks the number of mandatory positional arguments. Under default, these are extra values that make COArg count flexible. COFlags tells us, should we assign extra positional arguments to splat args? And should we assign extra keyword arguments to double splat KW args? And finally, we have KW only arg count, which is the number of keyword only arguments. Okay, switching topics a little bit, let's talk about scoping. And if I define x equals 100, global variable, and then I define this function, deffunc print infunc x equals x, let's call this function, but first let's print out what is the value of x before we call it, and then we'll call func, and then we'll print it. So when we call the function, when we call print here, we are looking for the value of x. Well, x, basically Python says, is x a global variable? The answer is yes. We retrieve the value 100, we print it out, and we get 100 back. Fantastic. So we get back 100. But when we call our function, what happens? Well, x now, is x a local variable? And now Python needs to go through its scoping rules. And these scoping rules are hard-coded in the language. LEGB, local, enclosing, globals, and built-ins. Python will always look through all of these here. And so Python is going to look and say, is x a local variable? The answer is no. So it says, okay, we don't have a function within a function. We'll ignore that. Is x a global variable? The answer is yes. And as you can see, we get 100 back. So far, so good. And then afterwards, of course, we get 100 back as well. Okay. But how does Python know that x isn't a local variable? Well, it checks in the attributes. It checks in CO var names. We've already seen this. Basically, Python could just take the x as a string and say, is x the string in CO var names? And if so, it's a local variable. But if not, if CO var names is empty, no. So because x is not in CO var names, it's not a local variable. Let's make things a little more complex, though. Let's say x equals 100, as before. But now, def-func, x equals 200. And then we're going to print the value. So what's going on here? Well, when we compile our function, when we define our function, Python notes to itself that x is a local variable. It sees that we have that x equal there, and notes to itself, aha, x is local. And so when we run print before x equals x, and then func, and then print, Python is again going to do its LEGB. So outside of a function, it's going to say, is this global? Yes, there is a global x. Its value is 100. And then we're going to run func. What happens then? Well, it's going to say, this x here, is it local? Yes, it is. It is a local variable. How does it know? Because in CO var names, x is listed. So it retrieves the local x, which is 200. And then finally, it comes back. The local variable is gone. We have just the global, and that's fine. And as we can see here, if we look at CO var names, sure enough, x is defined inside of CO var names. That's how Python knows. Notice, CO var names is populated at compile time, not at runtime. So what if we change our function a little bit? Exactly the same as before, except I'm going to swap these two lines. First, I'm going to print the value of x, and then I'm going to assign it to be 200. So here I'm going to, once again, print, func, and print. And what is the output I get? Well, it says before x equals 100, and then I get this. What is going on here? Unbound local error. Local variable x is referenced before assignment. What's going on? Well, we defined our function, and Python noticed when we defined our function that we have x equals in the function. If there's an x equals, that means that x must be a local variable. X equals anywhere in the function makes it a local variable. And so when we run the function, we get to that first line with print. Python says, is x a local variable? The answer is yes. And what is its value? Uh-oh. Unbound local error. Binding is a fancy way of saying assigning, like to assign to a variable name. And so unbound local basically means you have a local variable without a value. And this is weird because in Python, we're not used to having variables without values. And yet here we have it. We've sort of gotten to a bit of a corner and a bit of a fix. Now you might be saying, okay, who is going to print a value and then assign to it later? You'd be surprised. But a more common version of this problem is if I say x equals 100, and now I'm going to define the function. And look, I have your x plus equal 1 way at the top of the function. And many people would say, oh, we're going to take the value, the global x, 100, add 1 to it, and assign to a local x. But no, this is the same as saying x equals x plus 1. Python is going to notice the x equal, and it will say, aha, x is a local variable. And it's going to note that in CO var names. And then when it comes time to run the function, it's going to look up x plus 1. What is x? Is it local? Yes. What's its value? We don't have it. Unbound local error. Now, another thing we could do is use the global declaration. What does that do? It basically says we don't want to note x in CO var names. We don't want to list it as a local variable. So when we run this, it's going to be 100, 200, because we have assigned 200, but then it's going to also say 200. Why? Because now there is no local x. So when I assign to x from within the function, I'm really assigning to a global variable. By the way, even if it did not exist before, it is a global variable. And sure enough, we can see here, if we look at CO var names, it's empty. So Python uses LEGB to look for x, but it can't find the local, so it'll just go to the globals, which is fine. Let's use dis.dis to break apart these functions and see, both the non-global and the global version. So with a local version of x, without the global scope, without the global statement, we can see that the bytecodes include store fast and load fast. Store fast and load fast mean local variables. But when we include the global declaration in our function, notice now it has changed. The bytecodes have changed to be store global and load global. All right, time to get even more complicated. Let's talk about enclosing functions or enclosing scopes or nested scopes and functions. Meaning I'm going to define a function, and inside of that function I'm going to define another function. So my outer function, called outer quite appropriately, it has two local variables, run counter and total. And what I'm going to do is I'm going to add each time I run the inner function, I'm going to add to run counter. And I'm going to add to the total. Pretty great, huh? Now, this is sometimes known as a closure. Basically, if I run outer, I'm going to get back inner. I'm going to get that function object back, and I can assign it, as I do here to func, and then I can run func. And func will get an argument, x, and then we'll add to the run counter, and we'll print everything, and everything will be great, and when I run it, I get an unbound local error. Why? Well, if we just go back for a moment, you'll see that run counter plus equal 1, total plus equal x is exactly what I was talking about a few minutes ago. That basically that plus equal 1 sets us up for failure. Just run through these things. Okay, so what can we do instead? We can use non-local. Non-local tells Python, don't list these as local variables. But do realize they're not globals either. They're actually in the outer function's scope. These are local variables belonging to the outer function. And so when you modify them, don't modify them locally here. Don't look for globals, but modify the local variables in the outer function. Now, if this sounds weird, let's go back to the Python tutor, and we'll see a little bit of how this works. So we have here outer, a global variable pointing to the outer function. And we even see a stack frame, a time that we ran outer and got back inner, which we have then assigned to func. So we ran outer, right, that function object, and then we got back this function object, which has, it's referred to by func, and we also have inner referring to it. It refers back to the scope in which it was defined. How does this work? How does it keep track of the variables in that outer scope? Well, it has an attribute, co_free_vars. And co_free_vars contains two elements, run counter and total, the two variables that we declared with non-local. But it's not a one-directional relationship. It turns out that the outer function also knows, in its cell_vars attribute, it knows which variables have been defined and are referring to it. Okay, what have we learned? First of all, we've seen that def does two things. It defines a function object, and it defines that function object, assigns the function object to a variable. Secondly, function objects contain attributes, and these attributes both contain the bytecodes that were compiled from our function, and the hints to Python for running that function. Finally, attributes dictate behavior we take for granted. We don't think much about arguments. We don't think much about scoping, but the fact is these are really important to our functions, and they're all controlled by these function objects and by these attributes. If you have any questions or comments, I would be delighted to hear from you on email or on Twitter, and I hope to see you next year in Pittsburgh. Thanks for watching.